is, see, I'm going through it and I'm trying at least arduously to take it seriously and to wrestle with it and go through the details. And I personally didn't see anything in there that would say to a country who doesn't have our interests at hand. Who knows, even if our own government has our own interests at hand, who knows? But you understand what I'm referring to. I didn't see anything in there that would stop them from doing the same investigation that I'm doing. So what are you referring to? What do you mean? Can you talk around it?
I left out some of the secret sauce. I left out some of the secret sauce.
Okay.
So, welcome everybody to the Alien Scientist, and I'm just getting some clips out here. If you guys go to the link below in the description of this video, you'll find this interview that Kurt Jamungle here did with Salvatore Pais, the author of the U.S. Navy patents, which came out in about 2018. I think they actually came out in like 2017, but they weren't really made popular and advertised out there in the public until like 2018. And they've received a lot of criticism and skepticism and reviews. So I wanted to take this to go over some of the key timestamps and review some of this stuff, and then we're going to talk about this all and break it all down. So let's.
Okay, the whole idea is it leads to controlled motion of electrically charged matter from solid to plasma states, subjected to accelerated spin and or accelerated vibration via rapid acceleration transients. This gives rise to high energy electromagnetic energy fluxes, which are commensurate to high energy densities. Hence, it is possible, in my opinion, to achieve the Schwinger limit, that is, electromagnetic energy fluxes on the order of 10 to the 33 watts per meter square, which is commensurate to energy densities on the order of 10 to the 25 joules per meter cube. So, in other words, you can lead to something called quantum electrodynamic vacuum breakdown.
So let me translate. Basically, this is like the 1.21 gigawatts from Back to the Future. There's a limit where you actually break down space time at this what's called the Schwinger limit. When you pack enough energy density into a small amount of space, right? So there's two sides to that number. It's watts per meter squared, right, or meter cubed, right? So it's a volume. So a meter cubed is a volume. So it's you can make that really large. So if you want to, if your Schwinger limit say is 10 to the 33, right? You can either add more watts, which brings the number up, or you can compress the space and bring the volume down. And either one of those things in that equation, and someone really should go over this part, the middle part of this video, where they really. So the Superforce right here, about 58 minutes. This is the longest segment or single block of the video, and we're going to review that in some depth and detail here. And I'm going to bring some people on to sort of cross analyze some of the physics going on here, and we'll break this down as best as possible and introduce people to where they can find even more references in the physics literature with if they want to go and look this stuff up further to read deeper on the topic from a variety of scientists who have published extensively on a lot of these topics and where to find that that literature. So this is key, this 10 to the 33, right? So you either get a ton of energy or you shrink down that space to a really small space. And we'll talk about that in a second. So
When you achieve, yes,
I'm so sorry. As an aside for the audience, if you're not following what some of these terms are, don't worry, because as we continue throughout the podcast, I'm going to be stopping Sal at different points to explain certain terms, like even simple terms like what is a piezoelectric material. I know it's piezo, however people want to pronounce it. What is a superconductor? What is the Cooper pair? What is the Schwinger limit? And so on and so on. So this will serve, because this we're going to have another conversation. This will serve as a prelude to that conversation.
Correct, sir. And this is what I love about your podcast. Not only do you have a tremendous ability to understand your guest's work, and you really take your time, and I've never seen anybody.
Uh,
Like,
man, he gives Kurt some big props, man. Um, Kurt had a lot of homework to do after he came on my show, but Kurt's been a great asset in this field because he's got this persona and this his own thing going on, man. You know, I got my bad self. Yeah, thank you for the $20. That helps a lot. But I feel like, you know, as much as I'm on the chaotic evil side of the spectrum, he's on the, you know, good. He's on like the you know, good. He's on like the opposite side of the spectrum. And Kurt's cool, man. I really like him. He's definitely brings some great energy to this field, and he brings a lot of great interviews and stuff. Unfortunately, we came up with, I think, 3 or 4, maybe even 5 pages of questions for Sal. All of tech, really super technical related to his papers, and we all have to wait for part 2 for that, man. I just want to give a shout out to everyone. Danny Blanco out there, props. Lord Ludacris, Daryl Oster, the guy who invented the evacuated tube transport, before the precursor to like what Elon Musk tried to do with Hyperloop, but totally messed up. And we're going to bring him on to talk about that. Really, really awesome guy. I've been friends with him for like decades now, man. It seems over a decade. Yeah. Steve Cambion, Truth Seekers in the house. Devious Schematics, Brady Kramer. Thank you guys for joining, and it's awesome to have you all here. Yeah, this was a great podcast. Kurt did an awesome job, and we are all anxiously awaiting part 2 now. Man, this is going to part 2 is going to be amazing. Yeah, so we got the bad guys on this first, and sometimes it takes us to start talking about it to break the ice, because you know it's always the bad kid that walks out on the ice first and says, "Hey, come on, look, it's safe, come on," you know. So it's never the good kid first. So then the good kid sees all the bad kids doing it, and you know he's getting a lot of attention, you know. Yeah, so 36, happy 36, man, happy birthday, Ben Thrill. We got a birthday in the house. Rock on. Thank you again for that $20 super chat. That's awesome. So who's who in the video? So Kurt Jamungle is the guy who owns this channel, Theories of Everything with Kurt. And if you don't know about this channel, definitely need to get on this. He gets some really cool interviews, and he goes deep on a lot of the physics and a lot of the science involved in this stuff. He's just started dabbling in the UFO field and sort of the UFO physics and stuff. So we're giving him an introduction. Yeah, physics hurts a lot of this is really deep physics too. This is, you know, what hurt Einstein's head. Einstein, you know, sorry. You have to say it Einstein. That's technically, you know, to be properly correct. In fact, Sal Pais, he's Romanian, by the way. That's where his accent's from. And he the way he says Einstein up until one point, and there's one point in here actually he messes up and says Einstein and drops the Stein. But yeah, physics hurt this physics particularly hurt Einstein's head because he really couldn't wrap his brain around. Yes, Daryl Oster, that's et3.com, by the way, if people want to learn more about Daryl, and we're going to get him on an upcoming show too, to talk about some of these, you know, transportation inventions of the future, and that's really cool stuff. But let's get back into this gigawatts, that 10 to the 33 watts per meter cubed, and really get into the secret sauce of this. What he deems the superforce, you know. So let's
by non-linear medium.
Okay, so the nonlinear
Yes.
medium is the plasma, and that's inside the resonant cavity of this craft, and that is resonating because of the microwaves.
Yes, sir. Yes,
Okay.
because you, and as you add, as you accelerate in frequency of these, exactly how these frequencies are accelerated, I cannot speak on the podcast, but it is feasible to get this omega square effect rather than your regular linear omega. Because again, we're trying to counterbalance this q square term, this charge square term, because you don't. Again, it's hard to get that 1 coulomb of charge, as you yourself have remarked. So, but it is much better to get these high frequencies using either piezoelectrics or plasmas under certain structure.
Now, forgive me if I'm taking a while to come up with
No,
questions. It's
no.
only because I'm going through my notes and there's so much. Actually, for most people, I have them all on one page, but for you, they're scattered amongst.
So this is key, right? So plasma's under certain structure. All right. I want to take note of that key. You know, some of the key phrasing here when he says he's not spreading disinformation, right? He said Kurt asks him directly in this interview, and we'll get to that. He asks him if he's spreading misinformation, you know, right after this part about the secret sauce. In fact, let's go back to that.
I left out some of the secret sauce.
Okay.
Okay, now,
Yeah.
what do you make when people say, well, there has to be disinformation in it? Not just incomplete information, disinformation.
I did not write these patent applications, and I'm pretty sure the government did not file them in order to create false information. These were written to the physics of the effects that I was following through. That's all. They were not meant to scare off anybody. They're a new window into new opportunities. And it's quite possible, again, these have such commercial possibilities. They don't need to be weaponized. If indeed the Pais effect or the Schwinger effect or whatever you want to call it, if indeed this effect is valid, it could lead to a new world.
Oh.
Why not give it that opportunity? That's all. And I really wanted the Navy to have these, because if any of the contractors, if any of the companies that form the military industrial complex, if any of them have or will come up with these ideas, they would charge the Navy great amounts of money to make them feasible. If the Navy already has them, those prices can be talked down, be alleviated. And that's why I actually accepted no royalties for this whatsoever. None. Not 1 cent.
Yeah, but he's got a top secret clearance, and he said he's got a job now working for one of these contractors. So it at least got his foot in the door to some stuff and showed them that, hey, you know, I know some of this physics and I've got a lot of this figured out. So I assume he's working on this stuff for the military, and he's a very patriotic type of guy. Really strongly believes in the Defense Department, at least. United States Department of Defense, and you know, that's not a bad thing. You know, Defense Department isn't completely corrupt. There's some corrupt people in power and politicians and the money structures that run a lot of the stuff behind the scenes. But for the most part, our military is comprised of really good people that care about the community and care about the the future of humanity as a whole. Let's talk about some of this, the physics. This is some physics on cavity resonance, and you can find the resonant frequency of a cavity by this formula here, and where A is the speed of sound in that medium, so that would be the speed of sound in air, I believe. So it talks about some of the physics of cavity oscillations. And it's interesting that this cavity, in order for there to be this frequency, that there has to be an opening. And so I want to talk about the whole idea of flying saucers. Why the flying saucer shape? Why the if there's a cavity, that's some kind of cavity in the skin of this craft, from what can be deduced with the information that's been put out so far, right? So we have that metamaterial UFO piece, right? Everyone's seen this by now, that magnesium bismuth waveguide, essentially. Probably uses bismuth. We speculated that it used bismuth because it has the highest Lamar precession or spin on the periodic table, or one of the highest, and that it could be one of these waveguides that uses spintronics and hosts these types of high energy states, which are apparently required for this space-time warping effect. So I'm going to bring a friend of mine on. We're going to start bringing some people on. I posted the link earlier if people wanted to join. Looking for people that really know physics, and my friend Mike here is pretty good at that stuff. So Mike, welcome to the stream. We've been waiting for this Sal Pais interview since 2018. I'm so excited that this came out, and if we have any physicists in the audience who want to join us and sort of offer counterpoints or points to all this, please jump on.
Yeah, it's cool to finally see the guy out there. I don't know.
Yeah, there was a lot of controversy about him in the beginning. There were even people saying, that is he even a real person, questioning whether he was even an actual person or whether the U.S. Navy made him up. But now,
yeah, like I saw that on David Wilcock's thing, and I was like, yeah, that kind of makes sense. They would do something like that. But like now here he is, apparently. Yeah. Although,
and his story makes sense.
From the way he was talking, he struck me as more of an engineering type than a deep physicist. But I mean, he
even admits that
numbers, which is good. Like he starts with the dimensional analysis of things. That's always a nice place to start. Yeah. It was interesting around 26 around the 26-minute mark. He mentioned 1 coulomb of charge on rotating disks
Quite
at
high,
100k RPM. That was very interesting because back previous place I was working, I met a military guy. I don't think it was him. He had a different face to him, but like I mean, I met a military guy. I told him about a fuser project that I had considered but didn't have the time for. Back around 2018, but the patents got a priority date of 2016. But I suppose they could have had an extended patent from previous, and then they just redid it. Kind of, I don't know. It's interesting. It's a coincidence, perhaps, but I mean, I was thinking along a lot of the same lines in terms of his fusion reactor, like the way they had the cones and the repulsion between the cones is a dynamic effect from the plasma in between them. Because when you have like 6 giga electron volts and 100k RPM things rotating around, you need a significant repelling force. Like they're going to be attracted. I think I calculated something on the order of 30 giganewtons of force between these two cones. So if you don't have some AC signal in there stabilizing the plasma, it's just going to implode. but yeah, I mean, but he says there's this PZT surface, and that has an effect. Maybe that's interacting with the plasma in some special way. I don't know.
Velocity.
The engineering details of it. I mean, I didn't go too far into those specifically. I just had the general sense of how to construct such a fusor.
So let's break that down. So he uses this lead zirconium titanate, which is PZT. Lead is P on the periodic table. So this lead zirconium titanate, and it's like the needle on your record player. It produces like an impulse every time it has a bump. So I just imagine like my UFO disc, like a cymbal on my drum set, and it's vibrating at this and you have this surface coating of this lead zirconium titanate, and that vibrational effect creates all these voltages in that surface.
Well, I mean, he made it very clear in his talk that it's not just at least for the fusor and some of the other anti-gravity systems, it's the non-linearity of the plasma, or at least based on my models of gravity, it should be the non-linearity of the plasma.
So this
but he
plasma,
was saying that you get this high accelerations, impulse accelerations, and that breaks the Schwinger limit, which I suppose that could make sense in one way, because these matter particles, matter has very high energy density, approaching the Schwinger limit. Otherwise, it wouldn't be stable as matter. So
let's talk about that a little bit. So there's this crossover in physics between matter and energy, and that occurs in the realm of plasma physics. You know, when you get into solids, liquids, and gases, you can essentially think of it as degrees of freedom. So a solid has very little degrees of freedom. It can't move up or down. It can't rotate. So it has very limited degrees of freedom. That's the first class of materials are the solids. And then if you move up, you have liquids, which you gain a degree of rotational freedom. That additional degree of freedom is what allows the atoms to move around each other and turn from a solid into a liquid, because it's now the structure of the solid's allowed to, stay mostly intact, but it's allowed to conform now to its container and shape, and do a lot of other things geometrically. So that can be explained by this mathematically. Then if we add another degree of freedom, we get to a gaseous state, and then another degree of freedom, we get to this sort of plasma state, where you have all the degrees of freedom that light or energy has. And
I wouldn't describe it that way, but
okay,
sure,
correct me. What is this
you're adding more and more energy, and you have more and more density of states. I would say degrees of freedom. Yeah. As you add energy, you get higher density of possible states. Well, actually, that's not entirely true either, because low energy states become less likely at some point too.
But then don't you reach a limit where the states become so packed that they start conforming to the same wavelength, right?
No, that was different. That you're talking about the Prigogine effect, where they're saying that when you apply, if you figure out how to resonate certain nonlinear high energy far from equilibrium systems, then you get long range order in those systems. I wonder. I honestly wonder about the Prigogine effect, because some of it is like complex system dynamics, where you have islands of like, so you've got like in what was the guy's name, Stephen Wolfram's model, you've got like islands of reducibility, and that kind of concept, you can apply that definitely to plasmas. Like there's various states that have long range order, and there's a lot of states that are just completely chaotic. And if you know how to manipulate the plasma, you can get into these states where it's organized. And Yeah, I mean, they call that the Prigogine effect because they assume there's some really complicated dynamics that we're not necessarily aware of, nonlinear dynamics as well.
How do you
That
spell
allows it to be-
that?
Huh?
Prigogine? How do you spell this?
It was in Kurt's talk. I actually we mentioned it to him, and then he asked about it, which was cool.
Oh yeah, that's right. Yeah, that was part of
Prigogine.
Okay, I just want to spell it for the audience, Michael. So that's all. Just so because people don't know how to spell it, if you want to look it up on here. But yeah, I guess I can just tell them to go to Kurt's video and
Right. Anyways, however it is, the Prigogine effect. You're assuming that there's some complex nonlinear dynamics far from equilibrium that makes the math super complicated, and then you're just kind of saying, well, a solution exists for the steady state of this system, and we find that through experiment, and we assume that the math is solvable. Well, I mean, well, no, I mean, there's more to it than that. There's more to it, but I mean, in practice in engineering, that's kind of the way that's kind of the hand wavy thing people do on the engineering side. And I think there's a little more to this. Like we talked with what do you call it? We talked with Dan Sheehan and Remy Cornwall at great length about the Maxwell zombie systems. There are thermodynamic systems that, if you set them up properly, will reduce global like entropy over time. If you create
imagine if this effect not only creates this warping of space-time that can be used for anti-gravity, but it also has free energy involved.
Well,
we can pull energy out of the vacuum.
They don't have to be the same effect. It doesn't have to be the same effect. But
before we move on to the free energy stuff, I wanted to bring up this article, University of Bohm from March 24th. Physicists create this compressible optical quantum gas. It's another, photons in a mirror box type experiment, which is a kind of essentially what we're doing with these waveguide skin coatings.
I mean, any photon field can be considered a quantum gas, really.
Okay.
I mean, it's semantics a little bit, but yeah, they did it really well.
Islands of order, and it's got this point. But he points out that you get to this point where you start pumping more and more photons into the box, and then they start forming this like Bose-Einstein condensate type. They start cohering to the same wavelength because there's so many of them.
Well, let's not just gloss past all this stuff. So let's see, where was I? So we were talking about the Prigogine effect.
Yeah.
You organize the matter. These Maxwell zombies are a different thing, but at non-equilibrium, like when the math gets complicated, far from equilibrium, high energies, you could still have Maxwell zombie systems that persist, and I guess that's not a nonlinear effect so much, but they need to be considering that that's a possibility, and so far they haven't in that mathematics. So that's just another confounding factor right now. I don't know. I feel like when a lot of people mention, oh, non-equilibrium, far from equilibrium, high energy situation, like they're just kind of like hand waving, like we don't really know why this happens. Basically, it's like that's so like they're just saying, oh, the math is super complicated here. That's I mean, engineering wise, I understand. It's like you got to get things done too, but
so
typically,
I'm glad that you brought up Maxwell and the fact that right in the beginning of this,
they brought up Maxwell.
Yeah,
well,
well, Maxwell zombie, you brought that up.
Oh,
so
yes.
Yeah, you're absolutely right that Sal Pais right in the beginning, Kurt says, well, what was your inspiration? How did you come upon this and how did you get to this? And right away he mentions the whole Maxwell's equations and the Heaviside-Gibbs reformulation.
Well, that's a different thing, by the way, than the Maxwell zombies.
Yes, just so people know, just to clarify, people who want to get more information on that absolutely need to go watch this video. It's an hour and a half long, and it's a presentation from APEC number 2, actually, part 4 with Richard Van Durek. And this is a DARPA scientist that we were lucky enough to get on and have on to talk to us. And he's been on a number of Apex, background consultant, really smart guy. But go watch this video if you want a thorough scientific breakdown on exactly what Pais is talking about when he talks.
He's not actually so the Banduric effect is a generalization. It would be a generalization of Maxwell's equations. Actually, it's all of the higher order terms that are ignored in these current ones. Actually, that's true though. Sal Pais mentioned the higher order effect. So, or no, maybe that was Kurt.
Yeah, well, he
But
goes
either
through
way-
derivation in the first 15 minutes. He goes through that whole Heaviside Gibbs derivation. So it's worth it to at least watch the first 15 minutes of the Banduric presentation to go through that.
Well, I would say the generalization's interesting too, because if that immediately leads to a bunch of experiments you can try for yourself.
Yeah.
Assuming yeah. I mean, he goes into the discussion about it too. Let's see. I'm just going through my notes here that I took on the meeting just then.
Yeah.
Oh, I wish Kurt had mentioned the Froelich effect. That's I mean, maybe Sal asked him not to. I don't know, but the Froelich effect was basically a bunch of like Sal mentioned it, I guess. Jack Sarfati mentioned it. Hal Puthoff mentioned it. I was skeptical at first, but now I kind of get it. They're saying it's like a condensate, or it has condensate, like Bose-Einstein condensate like properties, but it's operating at much higher temperatures. And I mean, more recently, I found a whole bunch of research regarding high temperature superconductors using liquid mercury ammonia solutions and other ammonia solutions of metals, and that those superconduct due to high energy polarons, not the same as polaritons, but high energy polarons in the material medium. And the polar, not high energy polar, they're at the terahertz range, but the polarons are excitation quasi-particles in the matter, and the idea was that these can self-organize under Progogin's model into states that increase the Bose-Einstein condensate coupling between particles. So basically, if you increase the coupling term that makes the cool what's it, not cool
English, please. No, it's all right.
It's late. It's I don't usually stay up this late, to be honest. What's it? Cooper pairs. Yeah. So it increases the coupling in Cooper pairs.
So this is that whole superconductor theory, Cooper pairing, and
BCS theory.
Yep, BCS. So Cooper was one of the guys that came up with in BCS is, what is it? What are the three scientists?
So it's actually quite interesting.
Bardeen and Schreifer. Yeah,
it's very interesting because a lot of the high temperature superconductors are layered materials at the nanoscale, and for a long time people didn't know why. This explanation using polaron condensates, I think this is the most exciting one yet in terms of explanations of high temperature superconductivity, because it explains why you need a layered material, because when you have that layering, the electrons can travel in the sheets really easily, and the phonons can travel really easily vertically, but not vice versa. So something about that allows better coupling between the things. So yeah.
So that's kind of what's happening in the Cooper pairing, is the electrons form these Cooper pairs, which form these sheets in the superconductor material, which kind of do the same thing. And
that's Cooper pairing is standard BCS theory. That's just at sufficiently low temperatures, the phonons in the lattice couple with the electrons in such a way that the repulsion between electrons isn't complete. So there's some distance apart where these particles actually attract each other slightly. So then you get pairs of these things together because of that attraction force. But if you can take that phonon coupling and make it 1,000 times stronger, then you can have weird effects like that at room temperature. That's the idea.
So when I think of phonon coupling, I think like a mechanical vibration coupling. Yep.
No,
yeah,
no,
so-
phonons. Well, I mean, technically, maybe. So when they're talking about phonons in material science, they're typically talking about stuff in the terahertz range, like we were talking about. So it's not quite energetic enough to excite an electron out of an atom and make an electron hole pair. It's a little bit less energetic. So you get
Mhm.
quasi-particles, which are polarons instead of polaritons. Yeah. And then, well, actually, you get the polarons in layered materials mostly, just like you get
But
the polaritons in layered materials.
So don't you need a polariton to break that limit? Isn't that what we're trying to get to? Supposedly, or is this because
Well,
we're
I'm just
talking about
going
plasmas, right? And
these are just related condensed matter physics effects. I'm just going by what their research says. It's very interesting stuff, and it rings true. I wish there were more actionable stuff, but I can understand if they want to keep things secret, especially given the state of the world these days. Jeez.
so yeah, this is
but
interesting physics going on in condensed matter science and condensed matter physics. There's a lot
that's
of
where the forefront of everything is. I mean, ultimately, we
Yeah.
know that gravity emanates from matter. So when we went and did when we went and went with string theory and all of those theories, we're like, okay, we're going to take this piece of matter that's generating this field we don't understand, and we're going to look at the boundary around the matter and somehow intuit what this field is that it's emitting, which is, in hindsight, ridiculous. Like, just go look at the matter directly. What is it? Why is it emitting a gravity field? And so, like, and I mean, we're getting closer. We're getting very close to figuring that out. It's very cool to watch it happen. I mean, perhaps we already know. I'm not sure. Based on what I've seen, I think we're very close.
Yeah.
But yeah, I mean, he's using, what's it?
No, I'm just thinking, he talks about a plasma, but he doesn't give too many details. And he says, I left out the secret sauce. And I'm wondering if it has, that the plasma he's talking about are actually these surface plasmon polaritons, just because that was what Isaac Kemp wrote his PhD thesis paper on when I looked him up. And he was apparently doing classified research for the U.S. Air Force in a terahertz lab in Dayton, Ohio.
Well, see, there's a lot of overlap because polaritons allow you to emit photons within that. So there's different materials with different band gaps. If you're trying to create laser light, it's easier to do that with polaritons because you have actual excitations in the atom, which will give you laser light of a specific frequency. And if you tune your material properly, you can get terahertz frequencies. And then if you have some other material somewhere else that the light goes into that and produces polarons instead of polaritons, because it's a different material, it has different material properties. Maybe it doesn't have that band gap, or it might not have the energy levels required, but
Right,
it will
so
have a vibrational mode that is equivalent in the lattice.
Could this be the difference in why you have layering of, one isotope of magnesium, then a different isotope of magnesium on top of the bismuth layer, and then a different isotope of magnesium, on these alternating layers?
Well, yeah, I mean, that's planar weight disparity. I mean, if you go and look at superconductors.org, that guy shows it. I mean, tentatively. I mean, he hasn't had too many people replicate his research, obviously, but he demonstrates that he's getting results with things that have larger and larger planar weight disparities. So you have something that's very light, something that's very heavy in between each other. And what that does is it maximizes the impedance of those layers relative, or the difference in impedance of those layers. So if you look up Bragg reflectors, for light, if you have two materials with different refractive indices and optical properties, you're going to get lots and lots of reflections in between. So, and it depending on the thickness and impedance of those layers, also refractive index, you're going to get different frequencies of light that are reflected by that. So if you have essentially a Bragg reflector for phonons, then you're going to make those phonons bounce back and forth in those layers as much as possible. And in principle, that would maximize your coupling term between phonons and electrons in the lattice. So, I mean, that's what it would probably be, but that's kind of speculative.
Yeah, no, this is good physics to base off of. It's good speculation because it's educated guess. It's not just saying, yeah, like Mick West immediately saw this material and was like, oh, it's got to be something else, like fake and from something else. But whereas someone who's educated on some of this deeper, polaron and polariton physics might look at this material and be like, yeah,
we got to tell Kurt to ask more about the Froelich effect. I forget if I mentioned that already, but we got to do it. I mean,
yeah, well, he mentioned Froning, but he didn't talk about Froelich. So
Froning.
Let's talk.
Did he mention Froning?
Yeah.
What context was that?
So
Herbert, because I know Sal brought up Froelich, which was really good that he did, because it's key to the way his stuff works. At least in terms of getting high accelerations inside matter.
He also brought up
one of the easiest ways with coherent terahertz radiation. That makes total sense why they're talking about that way.
So where's the this is the guy, right? Froning from Kepler.
Yeah, that was
so
he was the guy, Alcubierre Froning warp drive, and he's done a lot of good research. But yeah,
he was he worked with NASA and did a ton of work with NASA and the European Space Administration. And when Alcubierre came out with that paper in '94 on warp drive, Froning worked with him on trying to actually build the warp drive.
Anyways, back to what you were saying. Sorry for jumping around a bit. You were talking about polaritons. You were talking about polaritons. He's talking about actual plasma, not polaritons in his systems. And it was interesting. It was interesting to me because, as you know, my idea of how gravity works requires at least a second order nonlinearity to be present in the system.
Okay, so let's talk about nonlinearities and linearities. What he described what a nonlinear medium, but I want to hear it from a material scientist. What's a nonlinear medium?
I mean, all the best scientists are mathematicians under the hood, but go check the Taylor's go look up Taylor's expansion.
Oh yeah,
Taylor series.
Yeah,
it's a good entry-level college way to look at it.
Yeah. We'll start with the Taylor series expansion.
The Taylor series, yeah.
So any function.
You see the terms in the Taylor series. You can describe any function on a finite domain with a Taylor series, and if you see each of these terms there's a second order term. There's a term that's like the square. It's got an x minus a squared.
Yeah.
Something cube. They have the square term. They have a cube term, a fourth order term. There's tons of.
By terms, he means each one of these f parenthesis things between the plus signs. So this is a term.
No, I mean the x minus a part.
This term.
This actually might not. Taylor series might not be the optimal one to explain this with, but
so a linear would just be these first two terms, and nonlinear would be include all these higher terms, right? Is that
Exactly. So basically, a lot of
Okay.
So what Ben Durick was saying is that the Maxwell's or the Heaviside equations, I guess, ignore all of these higher order terms, second, third, fourth, and because of that, they're limited. So that's what Ben Durick was saying. But also, the second order term, at least, is required for squeezing of quantum states, and that, from my model, is what I think gravity is. It's various entanglements related to squeezing, and like you can produce this squeezed object, which is it's a photon in a sense, but it has zero electromagnetic amplitude, and it's called a squeezed vacuum state, and that could well be the graviton.
very interesting? Because we get to he talked a little bit about Sarfati, and he touched on Sarfati and the work of Eric Davis, and
If
Eric,
you could refresh my memory, who was Eric Davis again? I focus on the research, not so much the names.
So Eric Davis is the one from Earth Tech who has been Hal Puthoff's partner for a couple at least a decade or so or more, and so he worked directly with a lot of with Hal Puthoff on a lot of this stuff, and he got some controversy around him concerning the Davis Wilson leaks, and like his talk about recovered craft and programs and that he was allegedly involved in but couldn't talk about. But in the end of this paper, he did a warp. I don't know if it's this one. Let me just see, because in a couple of So in a number of his papers, right, he talks about this Casimir effect and moving mirror, and he always mentions this optically squeezed laser light, and and gravitationally squeezed vacuum energy, and so he obviously this idea isn't unique and new. The idea of using metamaterials to enhance that C to the fourth over G, big G term,
Right.
that comes from if we go to the Estes Park conference.
Well, actually, if you look closely at what Sal Pais said in his talk, it's actually quite interesting. He demonstrates that the G fourth term relates to matter in a very fundamental way. Where was it again?
I should download this and repost this, but I'm going to post this here if people want to go check that out too. That's the where Sarfati and Keith Wanser go over, their idea of using these nonlinear metamaterials to, and the whole idea of maybe using terahertz, that high frequency light radiation to achieve this limit and break that.
I mean, now that all this stuff is out, it makes a lot more sense. Here's hoping there's something to it, but so let's see, vibration. I'm just looking through my notes more. I was glad to hear he watches Eric Weinstein's stuff and Kurt's podcast. That was pretty cool to see. He's a fan of those guys. Sal Pais was.
So I should be typing. I can just say this. So Kyle was asking on that last thing with the Taylor series.
Oh,
Prime is the prime denotes a derivative. The double prime denotes a second derivative. This to the third.
As I mentioned, this isn't the best series expansion to explain this with. There's like all sorts of series expansions. There's like, what is it, Lorentz series? There's Taylor series. There's a large variety of them. Fourier series, Laplace series. I forget, but anyway, the higher order, F prime is the derivative, F double prime is the second derivative, so on and so forth, and there basically the. As I mentioned, this isn't the best example because this is like for taking an approximation of a function around a particular point, but the x minus a term is kind of like if you have some amplitude of like if you have a nonlinear optical crystal, the intensity if your intensity of your light is high, then the intensity squared term of the photonic behavior will become relevant. And then at higher energies, the intensity cubed term will become relevant. So typically these higher order terms are small, but then once the intensity of the light becomes large, they become relevant to the equation, and you can't just say they're negligible. I mean, you guys, Jeremy, you showed that barium, that you showed the BBO crystal that could do, what was it? Phase conjugate mirroring. Yeah, you pull up that video. Yeah, that was a cool one. It basically shows at resonance, at high light intensity, the chi to the fourth term, the fourth order effect allows you to have this phase conjugate mirror effect, and it kind of intrinsically back calculates the scattering through the frosted glass once it's at resonance, which is like, that's an incredibly difficult quantum computation to do, and it's just kind of inherently doing it, which is impressive.
Yeah, let's watch this and talk about this, because how does this relate to? And then I want to get into some of the other scientists that were mentioned, like Ash
Oh,
Guitar.
barium titanate, not BBO. I was thinking of a different nonlinear optical crystal. Sorry, I interrupted you there.
No, that's fine. So they put a shadow mask in front of it to show the shape of this image, which is going to get diffused and scattered by the frosted cup that they're going to put in front of the beam. So he shows the focal point. At the focal point, he puts a beam splitter.
And that frosted glass scatters the image, so it's no longer projected. You can see when they turn the crystal, it goes out of resonance, and you can optically see that light bouncing around in there, or not bouncing around.
Yeah.
It's pretty impressive stuff.
Yeah, they knew about barium titanate since the 50s, man. I can go over some videos.
Yeah, they may have used it as an analogy for some stuff they found that was similar. Yeah, and then they cover this up.
Yeah, it goes out of resonance, so the all that image is now scattered randomly across this wall, and as it starts back calculating through the crystal, it goes into resonance with the literally all the atoms in the frosting of the glass, and then it reforms the image.
It's a very impressive thing. That would take hours on a computer. Took a minute on that thing. Photonic quantum computing needs to happen. Anyways, yeah, he was also mentioning how Jack Sarfati didn't think highly of his work. I don't know. I think he seems like he kind of wants credit for the whole thing. It's just kind of politics in the area. I wish people would work together more.
Yeah.
I don't know. I would.
Well, so I have an email from Sarfati, and Sarfati, like, he didn't respond back to me because I was like, I'd like to get you on to really talk about this, but his puff in this email, right? And I don't know if I want to show it, but he says Kurt and Sal Pais mentioned Eric Davis, me and Keith Wanser about 35 minutes in. Kurt also gives a nice quick summary of the basic Sarfati-Wanser idea, public since 2020, about making the G over C4 stronger with metamaterials. And, so that was made public at Estes Park in 2020. Again, at that link I posted earlier, if people want to go check that out.
Yeah, well, I mean, it is what it is. The G over C4 thing. It is key. If their model is correct, it's key because, well, I don't know. So their assumption that it creates low vacuum noise due to the Schwinger limit seems strange to me, because once you pass the Schwinger limit, you're creating real particles out of that excess vacuum energy. So you're not, to my knowledge at least, you're not distorting the amount of vacuum noise with that. The reason normal matter interacts gravitationally is because it has high energy densities, which affect the vacuum noise around the region of the particle. It's the self energy of the particle that creates its gravitational field, in a sense. So I don't see exactly why breaking the Schwinger. It seems to me like breaking the Schwinger limit would waste energy. You want to go up towards the Schwinger limit, but you don't want to break through it, because then you're just going to be like throwing away your energy as particles.
The secret sauce.
Secret sauce, yeah.
This needs to become a meme, dude. For real.
It won't.
People need to turn
Maybe
this
it
into
will, I
a
don't know.
meme.
I haven't been on the internet in a while.
I left out some of the secret sauce.
Hey, for those of you just tuning in, we're doing a whole breakdown and review of the Salvatore Pais interview that he did on Kurt Jamungle, and we're trying to formulate some good questions for part 2, which still hasn't happened. We got some good questions in already, and we're looking for more feedback from the audience and into some of that. This Ashkatar guy, let's talk about Ashkatar and black holes and
Yeah, that if that's true, that would be awesome, because now
if what's true.
Well, so if Ashkatar figured out a limit that basically removes singularities from black holes and requires quantum mechanics to work, that's a huge step forward for quantum gravity. If true, that would be awesome. I mean, I don't know.
Yeah, so currently there's this Rindler horizon, event horizon, right? Not the Rindler horizon, but that's something different. But
Ashkatar bound or something like that.
the Ashkatar bounds, yeah, and then that's sort of like the event horizon of a black hole, right? This
Well, he's saying that basically there's this superforce that once your black hole hits the Planck scale, this superforce becomes equal to whatever collapsing force was there and prevents it from going past that limit. I don't know. I guess that could be a thing. Why not?
is this? You think that
not
this
my area of expertise for sure?
I know, it just seems like there's a lot of people in the community that were like, "Oh, this could explain EVOs, this whole Superforce thing," and then it's the same thing that's going on in supercavitation.
Okay, so EVOs and supercavitation are, at least to my knowledge, not well defined. If someone can give me a good mathematical definition of what they mean by those things, I'd happily. But I mean, it seems very speculative as it stands. It's like, oh, X can describe EVOs. Oh, Y can describe EVOs, and then like they say EVOs are the reason everything happens, which it's not very scientific. Seems like.
Yeah,
Whatever.
it seems like maybe a more
Actually, Sal Pais mentioned something that I really liked. He was talking to a fellow, I forget. Oh yeah, around an hour 46 minutes, and 30 seconds. He talked about this guy who was really good at considering conditional possibilities. That's really important in general in life. Not even if you're just trying to figure out how gravity works. If you just take every issue in life and try to decide which way things are, on every possible issue, then there's a number of issues where you're making a decision without sufficient information for that decision to be like feasibly made. So it's important to oh, is it muted? I can't. Are you still there?
Yeah, I'm still here. I'm just going over. I'm just listening, man.
All right. Well, yeah. I mean, it's important in life to recognize when we don't have enough information to say things for sure, because like it's the hallmark of a true scientist to be able to entertain an idea without necessarily believing in an idea, if it makes sense. And it's something that I think we've lost a lot of in the past couple decades. And I do agree with Sal that, like,
right, it's like the same reason you can sit there and talk about flat spheres, but it doesn't mean that you believe in it.
It's like you with Bob Lazar, like.
Right, I could sit here and talk about Bob all day.
Feedback hurts a little, but like there's no realistically there's no feasible way to tell if he's lying or not. Not 100%. You can try to use statistics and put a whole bunch of data together, but ultimately it's all just I mean, you could have a pimp who was also involved in like reverse engineering spacecraft. Like if you can have someone like Jeffrey Epstein involved with all the scientists at MIT, like you can have someone like that who's actually, even if the world is controlled by nefarious people like that, then of course you would have a pimp who's reverse engineering UFOs. Like you can't there's no at the moment there's no feasible way to say for sure what Bob Lazar's thing is. But I mean, it's not particularly actionable at the moment. So let's just stick with the actionable stuff. I say is that's when you can't find a deciding factor.
We need obtainium, not unobtainium.
Deciding factor, if that makes sense.
We need obtainium, not unobtainium.
Well, yeah. I mean, just like when you can't decide on one thing, pick a direction to move that's 90 degrees different and go that way instead,
So
like even paramecium know that, although I think they do 30 degrees instead of 90 degrees.
It's just weird how it's like, we don't have government programs to fund any of this stuff. So and the only person that came close, really in the billionaire world was this pedophile guy, Jeffrey Epstein.
Yeah. I mean, like the system that exists is so messed up. You're like you can't just say based on someone's character. Like that's the thing. I think people get really mad at. What's his name's Stephen Cambion's channel. Like he just like tears all these people apart, and yeah, they're liars and whatever else maybe, but also all of the people in charge are lying, and it's a shame. But like maybe they're liars and they worked on this stuff. You can't say for sure with that. At least not like you can't say with mathematical certainty. Well, even really statistically significant certainty. But that's just the state we're in. So why, like, we gotta stop talking about all the little things and focus on the science. Because we're not gonna get anywhere talking about all the other stuff, really. Although that's what gets people excited on Twitter, because Twitter is literally designed to propagate that sort of stuff.
Mm-hmm.
But I don't know. It is what it is, and ultimately, well, yeah. I was interested. He mentioned he went to school in Ohio. That's right near Battelle, the Memorial Institute. That's very interesting.
Oh, Sal Pais did. So yeah. Right in the beginning of the Sal Pais interview, guys, he mentions that he went to school in Ohio. Right? Let me find
Was that the beginning? I don't know. I thought it was further in.
Or it was further in. Yeah, when he was talking about his educational background. So where did he go to school? In Columbus?
I forget.
Ohio?
He mentioned it like where did He mentioned around an hour 17 minutes.
All right. Well, let's go over a couple other key points.
Look carefully at the structure of general relativity formalism that's used by Einstein. And I shall not use Ricci or Riemannian curvature formalism. I'll use Einstein tensor. So G sub mu nu equals what? 8 pi big G divided by C to the fourth. The whole thing times T sub mu nu. That T sub mu nu again representative of energy density. But look carefully at that scalar constant. It has a term in it, C to the fourth divided by big G. Well, if you do the math, that term comes from a Planck energy divided by Planck length. So your Planck mass times c squared, the whole thing divided by gh bar divided by c cubed.
Someone needs to put this all out with like the equations up, you know,
Yeah,
to show all this. That would help visualize this a little bit better. Because
well, I don't know. I think that's specifically the part that Jack's probably mad about, because I bet Sal actually thought of it first, but since they were both in black programs, who knows who's going to get the credit, you know?
I know this is the crazy part of this.
But like, I mean, but I honestly, I'm agreeing with Sal here. Like, who cares what the credit is? Like, we need to get the technology out there. We need to get humanity off of the planet.
Put our egos aside and let's come together for humanity. You know.
Yeah, I mean,
about this.
I'd work for him any day, except he works for the government. I mean, if he can explain to me what the heck is up with the government, I'd happily work with him. But
yeah.
I'm a little hesitant just on that, but everything else he's saying seems fine.
Yeah, exactly. I've been deep in the black world and deep state and all that stuff for a number of years, and I love talking to these people to, you know, see if they know more about this and what's going on than I do, and there's some bigger picture, you know. I can't wait to that day I'm brought in like Will Smith to the Men in Black, you know, underground, and they're like, listen, you know, we made contact with an alien race back in 1940.
Oh yeah, Ghost Rider has an interesting comment here. Yeah, I bet it's related to that. It's probably related to specific resonances in the plasma that keep the plasma away from the surfaces. Actually, Robert Murray Smith has an interesting video about plasma fusion reactors on his channel that you might want to check out. I mean, the concept is similar to what Sal Pais' fuser patent is probably doing. But yeah, I mean, the secret sauce, it's probably a lot of engineering particulars. I mean, that's really, the principle can be simple, but obviously the engineering of anything remotely similar to this is going to be crazy difficult. But yeah, I mean, definitely, if you've got coherent terahertz radiation, you're manipulating phonons in layers of material, and you can get some pretty insane accelerations at terahertz frequencies out of particles. So, I mean, that's the thing he was saying, that, or I guess he didn't fully want to say. You're getting these high energy densities not only from your electrostatic fields or anything you've got set up, you're also getting these fields from the inherent fields of the matter. Matter has an extremely high energy density. So when you start oscillating these matter particles back and forth, now you're getting towards the Schwinger limit. Actually, I think they had a particle accelerator experiment where they smashed some. Was it protons? I don't remember, but they were using particles. They got a near miss, and because these particles were passing so fast past each other, they were able to generate photons just by their virtual particle fields crossing through each other, reaching the Schwinger limit, basically.
Yeah.
They were able to prove. There was a bunch of stuff online about that. I think it was on PBS Spacetime or whatever. It was on all the channels back a few months. But yeah, I mean, they were able to prove that, yeah, you can get towards the Schwinger limit with matter particles in certain orientations and at certain speeds. I don't know if you can get towards that at terahertz, but I mean, you don't need to reach the full Schwinger limit because we see matter emits a gravity field as it is. So if you can just change that effect, perhaps with terahertz, maybe that does something.
Yeah, it's interesting that there's a gap in the spectrum there, and that might be occurring due to it breaking the Schwinger limit when you reach that certain energy intensity.
I mean, I think it's just fundamental to how the matter interacts. So when you have crystals in a lattice, or when you have atoms, most of the excitation states that are feasible to reach are not in that terahertz region. So most of the excitation states for electrons are optical frequencies, roughly speaking.
So
Maybe
basically, that's what they're doing with these graphene sandwiches and these layered materials, is they're creating a environment that's conducive to actual production of these terahertz band frequencies, right?
Well, there's a lot of, so I mean, obviously there's some small band gap materials like zinc, cadmium selenide, sulfide mixtures that will laze. They'll make a terahertz laser. And then there's optical parametric oscillators, which you can make with a BBO crystal, for example. And you can, with optical materials, you can make an optical parametric oscillator well into the terahertz range. It's quite straightforward if you have the right optical table.
Yeah.
Equipment. So I mean,
they have that at right state, definitely.
They probably do. In order to work with terahertz, you also need all sorts of crazy detectors. Within my knowledge base, I've got part of those technologies, hopefully enough to work with, but we'll see. But yeah, I mean, it's not a difficult problem. You just need to get an optical parametric oscillator, set up the actually you use a Bragg reflector with that actually, and you adjust the angle of the Bragg reflector, and that changes the frequency that it emits. I forget exactly how it works. It's quite interesting. But yeah, I mean, there's ways to adjust the frequency. Optical parametric oscillators are very interesting actually, because unlike lasers, they're broadly tunable. You can have an optical parametric oscillator that can hit every frequency in the optical range, from ultraviolet all the way to infrared. It can do all of those. I mean, it's not as efficient as a laser, but a laser simply doesn't have the tunability. So
really, so you can
yeah, these go mid terahertz range. You can, some of the lower end stuff maybe not, but it all depends on how. It
also been recently demonstrated that a degenerate OPO can be used as an all optical quantum random number generator that does not require post processing.
Yeah, I mean, you can use them for a lot. Optical things are, honestly, we need photonic computers. We need, like, if you've seen the quantum computers that they made in China, it's all photonic crystals. That's what we should be doing. We're trying to make on-chip stuff just because we have semiconductor fabs. No, we should be using the optimal optical technology for quantum computing. China made their recent quantum computers the exact way that I would have, and I don't know why we missed that. Anyway,
back to Mike. If people want to join, I will start bringing people on, because we're about it.
Yeah, we're getting there. I'm almost done, honestly.
Yeah. A couple more things before Mike goes, though, too, because I want to talk about some of the personnel, and we'll get into some of this stuff after you leave. But while you're here and we're still on the technical details and stuff, Stuart Hameroff and this Penrose Hameroff model. I don't know. was this mentioned in this?
Yeah, they mentioned it, but Sal was like, you don't need that for consciousness, and I would tend to agree with him. Like, okay, you want to know the secret to consciousness? It's actually kind of simple. You literally, your brain is a neural net where some of your outputs are also your inputs. So that's simply saying that the stuff that your brain makes, it also shuffles those signals back into its inputs along with everything else. So that's why you're aware of your own brain's outputs. It's like that's not the weird thing about consciousness. Like the fundamentals of consciousness are not actually weird. It's all the like kind of stuff towards woo that doesn't have large data sets to support it yet, but could still be real. That's interesting to look at in terms of how that is done, but that's the fundamental of consciousness, at least mechanically, is just your outputs of your mind are your inputs into, and it's very simple to do that with a neural net. You just like people, it's just what do you call it? It's been done. It's been done actually with computer neural nets too. At this point, I forget what it's called. Whatever. It's not my field, I guess.
Yeah, I think if you built a this whole idea of this conscious observer, it's a mirror world. You know, this idea of what Heidegger called the Dasein. But I don't want to get into that. Let's get it more on. I want your scientific opinion. Superforce. Is it bunk? Is it real? What is this? Is this wording, to get around, like the secret sauce?
I'm gonna say no opinion yet. I haven't looked into it in the amount of depth that I would need to say yes or no. But I mean, as I mentioned, it's conditional possibilities. Sometimes it's better not to decide. Not immediately.
Again, you just entertain the idea and let's see where it goes. And there's no such thing as bad ideas. There's wrong.
Yeah.
There's wrong ideas, and there's more wrong ideas, and there's just not even right ideas.
Yeah, and in its current state, it's not useful to me, or at least I haven't looked at the math enough to understand the utility of that unification strategy. But in terms of practical engineering for devices, it's more towards the theoretical side for the moment. Oh, and I also noticed, like he said that towards the end he joined Space Force. Oh man, can we get like a character on the actual like the Space Force TV show to like be like this, like Sal Pais, but in Space Force? That would be
the scientist, the Navy scientist who knows all the secrets, the secret sauce. Oh my God, we got to do like a whole comedy thing on this. This is fire, man. This was well worth the wait, man.
Well, I'm glad he's out, and I would, before I go, I would just extend an invitation to Sal Pais to come to APEC and present his stuff. We'd love to have him on.
Yeah, APEC would be the place, because that way it's separate. So I'm gonna I want to play some of these key parts, and if you have any timestamps of key stuff that you want me to go over and play, stick around. So I'm gonna hit play for a minute though. I want to listen to Superforce.
Only that, but the Superforce equals the Planck force, and the Planck force does not have H bar in it, so it's non-Planckian in nature. It's classical, which means the Superforce, which equals the Planck force at the Planck scale, is the bridge between the world of the very large, namely general relativity, and the world of the very small, represented by quantum field theory. And
I mean, he's oversimplified it a little bit. I get it.
The bridge. That's what I want. Where's the bridge, man? Let's build the bridge.
He's describing it in. I wish he went into more detail.
I know. Well, that's what part 2 is going to be for. It's going to be the more technical one. Hopefully,
because he's describing it in like elementary school terms here almost. He's trying to like explain it to a kid, kind of. I wish he did more detail than that.
Superforce. I want to find the This is great, man. This is awesome. I want to find the transcript and find the part about what he says about Space Force, because I want to play that for people. So,
That was like somewhere at the end. I didn't get a timestamp for that, sadly.
well,
Oh, it was like
this is how I
it was
do
like
that.
third box from the end, and like he's
So,
got some. Kurt put in some timestamps.
this is what I do. Oh yeah, so Space Force.
There you go. Oh, cool. So there's a transcript that's made.
You can do a transcript, and you can do Control F, and you can basically search for
Oh,
what
that's
said
cool.
certain things. So that's
Nice.
A cool way to go. I should be able to
He
just
said he's
click
working
on this
there now.
one. Oh,
I
here
mean,
we
that
go.
might explain why Jack and he are not like on great terms. Because if he's working on the Trump side and Jack's working for like the deep state side, that would explain why they're not friends right now.
Yeah, Sarfati didn't he worked with Hal Puthoff and was brought in like on some CIA stuff back in, with some of that back in the day to
Oh.
basically try to figure out time travel and UFOs and a bunch of other.
I just hope they can get along in the future, because they're both smart and could help figure things out.
Yeah, man, and as much as Jack wants to brag, too, it's like let's get the engineers in the lab and build this and prove it. You know what I mean? It's all great and it looks all great on paper. I like the plan. I'm down with the plan. I'm down with what all these guys are talking about. I'm on it, and if we can get the team together to actually build this and promote this to get people interested in actually doing this, we're already getting a team together. We've already got some financial people interested and on board, because they see the potential in this. They realize, that this is the future of humanity at stake. And frankly, if you look around us, man, we're running out of time. We're running out, we're running out. It's like time's just ticking away, and every day we get, we're one day closer to either figuring this out and getting off the planet and fixing this situation with transportation and energy and everything else going on in the world, or we're one day away from that button getting pushed, where all our eggs are in this one basket. And whether it's nuclear Armageddon or an asteroid from space, a killer asteroid, we've got all our eggs in one basket, and we need to move to space.
Well, yeah, I mean, it's like I said to another guy recently, our technology is not commensurate with our wisdom right now. We've gotten very advanced, it's like Eric Weinstein said, we are gods but for the wisdom.
Gods but for the wisdom. My word, ain't that the truth? All right, guys,
yeah, I guess that's the end for now.
I think that's a good note to end on. What do you think?
Yeah, I think so.
All right, we'll open it up to the after party. Who wants to join and hang out behind the scenes? Here's the live chat, StreamYard link. We're going to answer some quick questions, and if anyone wants to join, and otherwise, have a good night, and we'll see you on the next one after part 2. Man, let's. This was super interesting, and I can't wait to see all the feedback and
Yeah,
really.
This was awesome. Yeah, this was this was highly anticipated by many people. This video, I'm glad he's out among us now.
And I can't wait to get into the metamaterials, and really, study. I'd love to get a piece of this material, man, that they gave to the U.S. Army.
Let's make some.
Let's make some of this. We could, you know how we've got some of the contract. We've actually contacted a number of metal coating and technologies. Metal.
Oh, did you ever hear back from what was it?
No, I haven't. I got to I'm gonna reach out to them again. Yeah, I'm not gonna really.
Yeah, don't mention the channel or anything. Just like get a random email, ask them for a quote on
I reached out to a number of people for a
Permanent.
quote, and I showed them this. I was like, "Is there any way you could make anything like this?" And even
I bet I could. I like if you get me. Let's see.
we could get it.
I could definitely try making this stuff. I
How
should
would
have.
we have to like powderize the magnesium and then separate it by centrifuge to get the different isotopes out? I mean, how is the best way to separate those isotopes?
Just buy it from someone else who does that. It's
Yeah.
these days laser separation is pretty
Mm.
efficient,
Mm.
but it's still not that efficient. It's better than centrifuges. It's just a huge pain, though. It's a huge pain. Oh, someone's asking for the after party link.
Yeah. So the StreamYard link after party. Let's join. Come on, and I'll see you guys there. There it is.
All set?
Yeah. Later, guys. Thanks for watching.